At the heart of the Milky Way lies a place almost no light escapes and no orbit stays simple. A dense, glowing center where stars crowd together thousands of times more tightly than they do near us. It is a region shaped by shock waves, newborn suns, drifting dust, and the quiet pull of a black hole 4 million times the mass of our own star. Tonight, on The Galaxy Scientist, we drift inward toward that hidden core and trace how a galaxy builds its heart, breathes through its spiral arms, and holds itself together in the dark. If this gentle journey feels right to you, a soft like and a quiet subscribe help others find their way here. Settle in now. The path begins slowly and warm. Right now, you are gliding through space at well over 400,000 miles per hour, carried by a quiet star that is itself racing around a supermassive black hole. That black hole rests in the deep heart of our galaxy, the Milky Way, and it is roughly 4 million times more massive than our Sun. Along the way, we drift past stellar graveyards where suns have died and through clouds of gas larger than entire solar systems, past newborn stars just opening their eyes and others being torn apart by gravity too strong for them to resist. We begin here, on Earth, even though this planet is anything but still. Our whole solar system is plowing through the galaxy at around 67,000 miles per hour, faster than any rocket human hands have ever launched. From the ground, it feels as if we simply circle the sun in a calm, predictable loop. But that quiet orbit is only one layer of the story. The sun is not sitting in place like a campfire. It is more like a speeding boat cutting across a dark ocean. And all the planets, including ours, are passengers pulled along in its wake. Picture the sun as the boat, bright and steady, with the planets trailing behind on invisible lines, all of us leaning into the same great curve around the center of the galaxy. We are not drifting aimlessly. We follow a vast track around the Milky Way's core, completing a single, slow lap only once every 230 million years or so. The last time Earth was in roughly this same part of its galactic path, there were no humans, no cities, not even dinosaurs. The continents were different, the air was different, yet the same galaxy was already turning. As we ride around this galactic circle, we are not gliding along a flat rail. The solar system bobs gently up and down through the galaxy's thin disk, like that imaginary speedboat, rising and falling over long, slow waves. Roughly every 33 million years, we pass through the crowded midplane of the Milky Way, then climb a little above it, then sink a little below. Some astronomers wonder whether these crossings might be linked to mass extinctions on Earth. When we move through the dense galactic disk, we wade into thicker currents of cosmic radiation, more wandering asteroids, and tangled gravitational fields that can disturb the delicate orbits of icy bodies in the outer reaches of our system. It helps to imagine the galaxy as a city. Sometimes, our solar system sails through the quiet suburbs, where there is mostly empty space between scattered stars. At other times, we pass nearer to the busy downtown districts, where stars, gas clouds, and fragments of rock crowd the sky like lights and traffic. For the moment, we drift in a calmer neighborhood where life had time to take root on this small blue world. Even here, in this relatively peaceful district, we are not traveling alone. Our entire solar system sits inside a vast bubble of hot, thin gas that extends for more than 1,000 light-years in every direction. You can think of it as a hollow, invisible shell wrapped around us. Long ago, a generation of massive stars lived and died in this region, When those heavy stars reached the ends of their lives, they did not grow old quietly and fade. They erupted as supernovas, brief and furious, each one releasing more energy in just a few heartbeats than our sun will shine over its entire 10 billion-year lifetime. Those explosions swept the surrounding space clean, pushing away most of the dense gas and dust that once filled this part of the galaxy. What remains is a spacious pocket that our solar system is now sailing through. Without this protective hollow, Earth might have grown up in a much more crowded and dangerous environment, wrapped in thick clouds of gas and hammered by stronger cosmic radiation. In such a place, it might have been far harder for gentle oceans, fragile atmospheres, and living cells to persist. In a way, we are living inside the memory of those ancient stellar deaths, cruising through a cavern carved by violence that has long since cooled into silence. When you look up at the night sky, you are looking outward toward the walls of this bubble in every direction. Many of the stars you see glittering there sit far beyond the shell's edge, shining through the thin boundary of our cosmic chamber. It is a bit like riding in a glass submarine through a deep ocean, the darkness outside endless, while we move inside, a protected compartment, shaped long ago by storms now faded into calm. Beyond the bubble's gentle walls, the galaxy is full of structures and forces so vast they make our whole solar system feel like a small lantern in a cathedral. Just past the edges of our bubble, the gas and dust of the Milky Way begin to thicken again. This is where the next landmarks lie, in regions where matter gathers and folds in on itself, and where new stars are kindled in spectacular fashion. Astronomers call the hollow around us the local bubble. It stretches across more than 1,000 light years, and our solar system is like a dust mote drifting through its center aisle. But this wide emptiness was carved by fire. Sometime between about 10 and 20 million years ago, a cluster of very massive stars shone here. Each one was at least several times heavier than our sun. When such stars burn through the fuel in their cores, they cannot settle into quiet old age. Their cores collapse. Their outer layers are hurled into space, and for a moment, they outshine whole galaxies. Those are the supernovas, bright scars in time. And they did not occur just once. One after another, over millions of years, stars in this region reached that final, explosive moment. Each blast sent a shockwave rolling outward, an invisible tsunami racing through space. As those waves expanded, they swept up gas and dust, pushing it away from the center of each explosion. Where several supernovas erupted in the same neighborhood, their expanding shells collided and merged, scooping out larger hollows. Given enough time and enough explosions, astronomers call the result a superbubble, an enormous cavity blown into the galaxy's gas. Our own local bubble is one of these, still slowly swelling from the combined push of long faded blasts. You can imagine it by thinking of stones dropped into a still pond. Each stone sends out circular ripples, spreading wider and wider, overlapping and colliding. Here, the stones were exploding stars, and the pond is the thin gas between them. Their overlapping waves carved out regions of relative emptiness and left behind surrounding walls of compressed material. The walls are not smooth or bare. They are made of gas, heated to well over 1 million degrees by the energy of those ancient supernovas. The gas is incredibly thin, so airy that a little cube of space the size of a sugar cube might hold fewer atoms than the best vacuum chambers on Earth. Even so, the gas glows with soft X-ray light, a high-energy glow that our eyes cannot see, but that orbiting telescopes can trace. Our solar system does not sit at the center of this hollow. We are closer to one of its sides, drifting slowly toward a place where the bubble's wall is thickening with cooler gas and fine dust. If we could wait around 5 million years and watch in fast forward, we would see our solar system nudge its way through that wall and emerge into a denser region of the galaxy. Beyond that point, the thin veil of hot gas that now wraps us, deflecting some of the cosmic rays that would otherwise spray into our neighborhood, will give way to regions where the gas is denser and the magnetic fields more tangled. Earth's atmosphere will be brushed by more high-energy particles from deep space. Some scientists quietly wonder whether such changes could stir climate shifts or even play a small role in large-scale extinctions over the long history of life. For now, though, we drift inside this cosmic harbor, sheltered by the aftermath of stellar death. The very explosions that might once have sterilized young planets here, burning away any fragile beginnings of life, have also cleared out a calm pocket where life on Earth later had room to grow. As we move through the local bubble, we are heading towards something remarkable. Ahead of us, in roughly the direction our solar system is traveling, lie the stellar nurseries where new suns are being born even now. Only a few hundred light years from Earth, in the dark lanes of the constellation Orion, a quiet miracle is unfolding. Enormous clouds of gas and dust are collapsing under their own gentle but relentless gravity. Deep inside these thick, cold cocoons, the material gathers into knots, and those knots into dense cores, until new stars ignite for the first time. The nearest star-forming region to us is so active that, if our eyes could see in infrared rather than visible light, that patch of sky would blaze brighter than any familiar star. Astronomers call this busy nursery the Orion Molecular Cloud Complex, and it truly is a factory for making suns. Picture a cloud so large that light itself needs years to cross from one side to the other. Within it, filaments of gas stretch like misty bridges, and clumps of dust drift like seeds waiting for a season. Over long stretches of time, the whole structure slowly contracts, much like a giant hand gently squeezing a sponge. As the cloud shrinks, the material in its center grows hotter and more compressed. When the central temperature and pressure climb high enough, something extraordinary happens. Nuclear fusion begins. Tiny atomic nuclei are pressed together so tightly that they join, releasing energy in the process. In that instant, a new star switches on. Its surface begins to shine, and its core settles into the steady, burning balance that will last for billions of years. But the birth of a star is not a quiet affair. Once a young star has lit, it sends out strong winds of particles, streaming away at hundreds of miles per second. Those stellar winds shove aside the surrounding gas, carving out hollows, bubbles, and long, sculpted cavities in the parent cloud. Seen from afar, these shapes can look like arches, pillars, and curtains, as if the star were an artist chiseling its own alcove from the fog that made it. Some of the newborn stars in the Orion complex are especially massive and wild. They pour out so much light and energy that they turn whole regions of their birth cloud into glowing nebulae, lanterns of gas visible across thousands of light years. The entire process, from the first gentle collapse of the cloud to the quiet settling of stable stars, takes millions of years. Watching such a birth is like watching a flower bloom in slow motion, except this flower is larger than our entire solar system and, in time, will burn brighter than 1,000,000 suns. But even inside the same vast gardens of gas and dust, not every fold of cloud wins the long, slow race to become a shining star. Some knots collapse partway and then stall, never quite hot or dense enough in their hearts to fully ignite. They become brown dwarfs, almost stars that glow with a soft, hidden warmth in infrared light, visible only to special instruments. Others are not even that fortunate. They are shredded and scattered by the fierce winds and radiation from brighter, more successful neighbors, pulled apart before they can ever truly gather themselves. What makes all of this even more tender is that stars rarely arrive alone. When a giant cloud of gas and dust caves in on itself, it usually does not form just one star at the center. It fractures, splits into many pieces, each fragment becoming its own sun. In those early days, the newborn stars are siblings, cradled close together in the same cosmic nursery, sharing a neighborhood wrapped in the remains of the cloud that made them. For millions of years, these young stars live side by side, like children growing up in the same small town. But the galaxy is never still. Slowly, gently, the pull of the wider Milky Way tugs at them from every direction. Their orbits shift, their paths diverge, and the once tight cluster loosens. Over long stretches of time, the siblings drift apart. The family dissolves into the wider star field, until only memory and shared chemistry tie them together. Our own sun began its life in such a cluster, in the company of thousands of other young stars, a little more than 4.5 billion years ago. For a while, they lit up the same patch of the galaxy, dancing through space as a group. Now those brothers and sisters of the sun are scattered far and wide, spread across the Milky Way like seeds caught in a slow wind. They hide among hundreds of billions of other stars, their original cluster long dissolved. We do not know where they are. The galaxy has scrambled the clues so thoroughly that, for now, they are almost impossible to pick out. Still, somewhere out there, orbiting quietly, are stars that were born from the same cloud as our own. Their planets, if they have any, would be made from the same kind of material, the same ancient dust. In a way, the star formation we see today in nearby regions is like a mirror held up to our own distant past. When we watch those clouds collapse and those young suns ignite, we are peeking back through time at a process that once cradled the beginnings of our solar system. There is something intimate in knowing that every element in your body, except for the simplest ones like hydrogen and helium, was forged in stars. The calcium in your bones, the iron in your blood, the oxygen that fills your lungs with each gentle breath, the carbon that shapes your cells, these did not appear out of nowhere. They were cooked in stellar furnaces, in the hot, dense cores of ancient suns that burned long before Earth existed. When those stars exhausted their fuel, some swelled into red giants and puffed their outer layers into space. Others ended more violently, collapsing and exploding as supernovas, tearing themselves apart in bright flashes that enriched the surrounding gas with newly minted elements. Over time, that enriched gas collected again into clouds. From those clouds, new stars and planets formed, including our own. You, sitting here in the quiet, are made of recycled starlight, assembled from the ashes of cosmic giants. It is not just poetry, it is chemistry, written into every atom of you. These busy stellar nurseries we have been drifting through are only the first layer of the Milky Way's architecture. They sit inside something larger, a pattern that binds many such regions into a single flowing shape. Our solar system is not parked at a random address. We are woven into a structure so vast that early astronomers, staring up with their first telescopes, had no clue it was there. This structure is called the Orion Arm, or the Local Arm. It is a smaller spiral arm of the Milky Way. stretching for thousands of light years in both directions from where we are. We do not simply ride alongside it like a car driving next to a guardrail. We are part of the arm itself, one small knot of matter inside its broad, curling lane. If you imagine the Milky Way seen from far above, it might resemble a giant hurricane frozen in starlight. The bright spiral arms in the pictures are like the storm's sweeping bands, but instead of water droplets and clouds, they are built from stars, gas, and dust. Many spiral galaxies have 2 or 4 major arms, the dominant swirls that define their shape. Yet there are also smaller arms and little branches, side roads and spurs, leading off the main galactic highways. For a long time, astronomers believed that our sun lived in one of these tiny offshoots, a small spur connecting 2 more important arms. It gave the impression that we were tucked away in a quiet side street of the galaxy, somewhere between the big thoroughfares. But as telescopes and surveys improved, a different picture emerged. By carefully mapping the positions and motions of many stars, scientists realized that the Orion Arm was not just a minor spur. It was larger and more substantial than they had thought. Now it looks as though this arm stretches for more than 20,000 light years, long enough and rich enough in stars and gas to count as a significant structure of its own. Far from being a cosmic backwater, our region is a busy segment of a major galactic road. Some of the most familiar patterns you see in the night sky belong to this same arm. The brilliant stars of Orion, the graceful lines of Perseus, the wings of Cygnus, many of the glowing nebulae and dark molecular clouds where new stars are being born, including the Orion complex we just visited in our thoughts, are all tenets of this shared arm. You can think of the Orion Arm as a gravitational river. Gas and dust flow along it, guided by the combined pull of countless stars and the larger gravity of the galaxy's disk. As this material streams through, it piles up in certain places, becoming dense enough for new generations of stars to form. That is why spiral arms often look brighter and richer. They are places where star formation is more active, not rigid structures carved into the galaxy. In fact, spiral arms are not permanent walls or solid spirals at all. They are more like traffic jams on a highway. Cars move in and out of a traffic jam, but the jam itself can stay in roughly the same place, a pattern made from motion. Likewise, stars and gas clouds orbit the galactic center, and as they do, they bunch up in regions where gravity and density waves slow them down slightly. Those bunchings are what we see as spiral arms. Stars, including our sun, flow into these arms, spend some time within them, and then drift out again into the more open spaces between. Over the course of its life, our solar system has probably moved into and out of spiral arms many times. The difference in density between the arms and the gaps matters. In the denser environment of an arm, gas clouds feel more pressure. That compression can nudge them into collapse, triggering new rounds of star formation. And once massive young stars appear, their intense light, winds, and eventual supernova explosions can either interrupt nearby star birth or spark fresh collapses in neighboring clouds. Right now, our sun sits about halfway between the galaxy's bright core and its distant outer edge, in a region astronomers sometimes call the galactic habitable zone. It is a gentle phrase for a fragile balance. Closer to the center, the crowding of stars becomes extreme. Radiation is harsher, supernovas more common, and gravitational forces more tangled. Planetary orbits there can be disturbed more easily, and environments can be more hostile to complex life. Farther out, near the galaxy's rim, conditions swing the other way. There, stars tend to be poorer in heavy elements. the ones needed to build rocky planets like Earth. Without enough of those ingredients, it is harder to make solid worlds with crusts, oceans, and long-lived atmospheres. Our address in the Orion Arm seems to fall in a cosmic sweet spot, not too close to the dangerous center, not too poor in materials at the edge. In this middle band, radiation is moderate, heavy elements are abundant enough, and the pace of star formation is busy, but not overwhelming. It is as if our solar system grew up in a part of the galaxy that is lively yet not chaotic, the kind of neighborhood where fragile things have a chance to persist. Even in this relatively calm zone, though, we are never truly still. When you sit quietly, you may feel motionless, but you are wrapped in many layers of movement. The first is the easiest to picture: Earth spinning on its axis. At the equator, that spin carries you along at a little over 1,000 miles per hour, turning day into night and night into day. On top of that, Earth is orbiting the Sun, racing along its path at about 67,000 miles per hour. That is your second layer of motion, a vast yearly circle that your body traces every time you blow out birthday candles or mark another turn of the calendar. Most of us have heard of these motions, at least in school. They sound fast, and they are, but they are only the opening notes in a much larger song. The entire solar system, sun, planets, moons, and distant icy debris, is itself moving around the center of the Milky Way. Our star, carrying us with it, orbits the galactic core at roughly 514,000 miles per hour. If you could somehow step outside all of this and watch the solar system from a fixed point in space, you would see it streak past like a glowing arrow. Every second, purely from this galactic rotation, you travel more than 140 miles through space. While you pause between breaths, while you let your eyelids grow heavy, your address in the galaxy is changing at a rate the human body cannot feel. Yet, even that is not the whole story. The Milky Way itself is not anchored. It is moving through the larger web of galaxies, tugged by their combined gravity. Our galaxy is drifting, or maybe more accurately, falling toward a nearby giant assembly of galaxies called the Virgo cluster, at a speed of over 1 million miles per hour. And the Virgo cluster, along with many other clusters, is being drawn toward an even more massive, mysterious region nicknamed the Great Attractor, a gravitational basin on scales that are hard to imagine. When you add up these layers, Earth's spin, Earth's orbit, the Sun's journey around the galactic center, the Milky Way's fall toward greater structures, your total speed through the universe reaches roughly 1.5 million miles per hour. It is a number so large it loses all feeling, until you shrink it back down to something simple. In the time it takes you to read a single sentence, you have already traveled hundreds of miles through space, and yet you feel none of it. There is no cosmic wind tugging at your hair, no sense of acceleration pressing you into your chair. Everything around you, the air, the buildings, the people you love, the oceans and mountains, the moon in the sky is riding along with you, sharing the same intricate path. Because you are moving together, your body reads it as rest. This quiet, shared motion does more than give us impressive numbers. As our solar system makes its slow circuit around the galaxy, it passes through different environments, like a ship alternating between crowded harbors and open sea. Sometimes we find ourselves within or near a spiral arm, where star formation is active and background radiation is slightly higher. At other times, we slip through the calmer regions between arms, as we are doing now, in a relatively peaceful suburb of the Milky Way. The pace of our galactic orbit also sets a kind of rhythm. One full trip around the Milky Way takes about 230 million years, a span astronomers sometimes call a galactic year. Since Earth first formed, our planet has completed only about 20 of these immense years. The last time we passed this same general position along our orbit, the most complex life in Earth's oceans consisted of simple marine creatures, with no forests, no birds, no four-legged animals on land. Dinosaurs, mammals, and humans have all emerged and changed and wandered during our current long, turning journey around the galaxy. And this slow rhythm of our path is just one strand in a larger motion. The Milky Way does not turn like a solid wheel. Its spin is more like the slow swirl of cream in coffee, different parts sliding past each other at different speeds. Closer to the center, stars race along their orbits more quickly. Farther out, near the galaxy's edges, they move more slowly, taking their time. This uneven, or differential, rotation is part of what keeps the Milky Way's spiral shape from fading away. If every star and cloud completed its circle at exactly the same pace, the graceful arms you see in those familiar galaxy pictures would wind up tighter and tighter, like a coiled spring, and blur into a smooth disk in only a few 100 million years. Instead, because the inner parts move faster than the outer ones, patterns of density and motion are stretched and maintained, letting the spiral arms linger for ages, always changing yet somehow still there. Deeper toward the galactic center, these orbital speeds grow even more intense. Gravity grips harder, paths curve more sharply, and the consequences of rotation become stranger. In those inner regions, the same simple act of moving in a circle can create some of the oddest and most extreme objects the universe has to offer. Between the bright stars that decorate our night sky, there is another population, much quieter and far more eerie. The cosmic dead, scattered all around our part of the galaxy, are the remnants of stars that lived their full lives and burned out long ago. They no longer shine like ordinary suns, yet they endure as compact, exotic corpses, so strange that they could easily be mistaken for inventions of science fiction. They are invisible to your eyes when you look up from your window, but they are everywhere, woven into the darkness, and some of them are among the most dangerous things in existence. The most common citizens of this stellar graveyard are white dwarf stars. When a star like our Sun exhausts the fuel in its core, it sheds its outer layers into space, leaving behind a hot, dense heart. That leftover core is the white dwarf. Imagine taking a little more than half of the Sun's mass and squeezing it into a sphere roughly the size of Earth. The matter inside is so compressed that a teaspoon of it would weigh as much as a car. The nearest white dwarf neighbors us within roughly a dozen light years, making it one of the closest stars beyond our own Sun, though you would never notice it without a telescope. Newly formed white dwarfs begin incredibly hot, with surface temperatures over 100,000 degrees, glowing fiercely in ultraviolet light. But with no fresh fuel to burn, they slowly cool and dim over billions of years, like embers fading in a vast cosmic fireplace. Some of the oldest white dwarfs in the Milky Way have been cooling for so long that their surfaces are now cooler than the Sun's outer layers. These ancient remnants are like time capsules, preserving clues about stars that died when the universe itself was much younger, long before Earth took shape. Yet, white dwarfs are not always as quiet as they seem. If a white dwarf orbits close to a companion star, its gravity can begin to pull material off its partner, stealing gas from the companion's outer layers. Little by little, that stolen matter spirals down and gathers on the white dwarf's surface, forming a thin, unstable shell. When enough has piled up, the base of that layer grows hot and dense, and suddenly, A thermonuclear reaction roars to life. The result is a nova, a surface explosion that makes the star flare dramatically brighter for a while. The blast blows away much of the accumulated material, and then the system can start the slow theft all over again. In this way, a seemingly dead star can flicker back into dramatic outbursts, not by reviving its core, but by igniting borrowed fuel. Stranger still are the neutron stars hiding in the same galactic neighborhoods. These are born from heavier stars, ones at least several times more massive than our Sun. When such a massive star runs out of fuel and explodes as a supernova, its core collapses under its own gravity with ferocious speed. Protons and electrons are crushed together to form neutrons, and the whole mass is squeezed into an object so dense it defies ordinary imagination. A neutron star is so packed that a sugar cube-sized piece of its material would weigh billions of tons more mass than entire mountains on Earth. The whole star, more massive than the Sun, is crammed into a sphere only on the order of a dozen miles across, roughly the size of a city. It is like shrinking an entire star into something that could fit inside a small valley. Some neutron stars spin incredibly rapidly, hundreds of times each second, while powerful magnetic fields channel streams of particles and light out from their magnetic poles. These beams sweep through space like the light from a lighthouse. If one of those beams happens to cross Earth, we detect it as a series of regular pulses in radio waves or other wavelengths. Astronomers call such objects pulsars. Their timing is so steady that some pulsars rival the precision of atomic clocks, ticking away with almost unbelievable consistency. The fastest spinning pulsar we know of rotates more than 700 times every second. Its magnetic field, like that of many neutron stars, is mind-bendingly strong, trillions of times stronger than Earth's field. If, by some impossible magic, a neutron star were placed where our moon is, its magnetic field would be strong enough to erase every credit card stripe on the planet. To come within a few hundred miles of such an object without protection would be instantly fatal. The field would tug at the charged particles in your body, disrupting the delicate electrical signals in your nervous system. Muscles, including the heart, would no longer receive clear instructions. It is a kind of danger that has no counterpart in everyday life, a quiet, invisible force strong enough to unmake the body's ability to function. These stellar corpses are not just curiosities to catalog. They are natural laboratories for physics pushed to extremes we cannot reproduce on Earth. In white dwarfs and neutron stars, matter is crushed, heated, and magnetized in ways that test our understanding of the laws of nature. By studying them from afar, we learn how atoms behave under colossal pressure, how gravity and quantum mechanics dance together, and what becomes of stars when the long burning of their lives comes to an end. And yet, remarkable as these remnants are, they are only a small part of the Milky Way's story. Beyond the quieter sweep of our local arm lies a structure that makes our immediate surroundings feel modest. Farther along the galaxy's disk, another great spiral arm loops through space, the Perseus arm, one of the Milky Way's major branches. If our local Orion arm is like a pleasant, well-lit avenue, the Perseus arm is a roaring superhighway. It is packed with far more stars, gas, and energetic events than anything we have drifted through so far. Moving from our arm into Perseus would be like stepping out of a sleepy side street straight onto a busy interstate, where the traffic never stops and the lights never dim. Within this enormous structure live some of the most luminous, powerful stars in the galaxy. While our own neighborhood is home mainly to modest stars and moderate star-forming regions, the Perseus arm shelters stellar giants, Some of the stars here can be 50 or even 100 times more massive than our Sun, because they are so huge. They burn through their fuel at a furious rate, shining with a brilliant blue-white light in our telescopes. They live fast and die young, often lasting only a few million years before their cores collapse and they end in titanic explosions. The arm takes its name from the constellation Perseus, which lies in the same general direction in the sky when viewed from Earth. But the arm itself reaches far beyond the familiar pattern of stars you can see with your naked eyes. It stretches for many tens of thousands of light years, wrapping partway around the galaxy like a loose spiral of glowing thread. If you could shrink the entire Milky Way down to the size of a dinner plate, the Perseus arm would be one of the bold curves you would see winding outward from the center. What makes regions like the Perseus arm so intensely active is the way the galaxy's density waves shape them. As gas and stars orbit the galactic center, they do not move in a perfectly smooth distribution. Instead, the gravity of the disk creates patterns where material slows and piles up a bit, like those traffic jams we imagined earlier. Where the jam is thickest, gas clouds are more crowded together, compressed by the surrounding pull. As a cloud enters a spiral arm, it feels the increased gravity and the higher density of its neighbors. The cloud is squeezed, and that extra pressure can push it over the edge into collapse, forming new stars. Once those stars ignite, especially the most massive and luminous ones, they blaze with fierce radiation and strong winds, shaping the clouds that birth them, and sometimes triggering further rounds of star formation nearby. In this way, spiral arms become engines of stellar creation. The Perseus arm hosts some of the most spectacular star-forming regions known to astronomy. One of them is the Eagle Nebula, famous for its towering pillars of gas and dust where young stars are being born. These columns stretch over several light years, rising like stone spires in a misty landscape. Though they are made of material so thin you could not feel it if you were drifting through it. The intense ultraviolet light from nearby massive stars sculpts the pillars, burning away their outer layers and revealing the dense knots inside where new suns are still forming. Another celebrated region is the Rosette Nebula, a vast bloom of glowing gas, shaped a little like a flower from certain angles. Its red glow comes from hydrogen atoms that have been energized and stripped of electrons by a central cluster of hot, young stars. Those stars flood the nebula with radiation, heating and lighting the gas so that it shines in vivid colors captured by long exposure photographs. But the Perseus arm is not only a cradle for stars, it is also a stage for their most violent endings. The massive blue-white giants that live here end their brief lives in supernova explosions of staggering power. In a single event, they can release as much energy as billions of ordinary suns radiate over long periods. Some of these explosions are so bright that they can be seen from other galaxies across millions of light years of space. When those stars tear themselves apart, they do more than put on a light show. The blast waves stir and enrich the surrounding gas, mixing in heavy elements like carbon, oxygen, silicon, and iron, the very ingredients needed to build rocky planets, metal-rich asteroids, and eventually, perhaps, living chemistry. In this way, each death seeds the next generation, and the arm becomes both nursery and graveyard, creator and recycler. To travel through the Perseus arm would be to move through a vast construction zone on a cosmic scale. Everywhere around you, something would be happening. In one direction, great clouds of gas would be collapsing, hiding new stars in their depths. In another, an aging giant would be puffing out its last layers. Nearby, a cluster of young suns would be carving bubbles and caverns in their birth cloud. Farther away, the silent shock front of a long-past supernova would still be racing outward, sweeping up material as it goes. Radiation fields would be intense, bathed in high-energy light that would quickly strip life from any unshielded surface. Spacecraft without powerful protection would see their electronics damaged, their hulls slowly eroded by invisible particles. It would be a place of breathtaking beauty, shimmering nebulas, crowded star fields, brilliant beacons, and at the same time, a landscape of hazards, where the forces that create worlds can also erase them. Beautiful and quietly deadly, all at once. Deeper toward the Milky Way's heart, everything becomes denser and more intense. You can imagine looking up at a sky where the darkness is thin, where you no longer see single, lonely stars, but whole cities of them pressed together so tightly they blur into glowing clouds. As we drift further inward in our thoughts, we begin to pass through star clusters that hold hundreds of thousands, even millions, of suns, all born from the same ancient nursery of gas and dust. These stellar cities are among the most crowded and spectacular places in the galaxy. The most massive of them are called globular clusters, round swarms of stars that are older than almost anything we know. They formed when the universe itself was still young, more than 12 billion years ago. A single globular cluster can contain around 1 million stars, crammed into a region only a few hundred light years across, like a bright sphere of starlight hanging in the dark. If Earth orbited a star near the center of such a cluster, our nights would never be truly black. Instead of a few bright stars and quiet constellations, the sky would be filled with thousands of suns shining brighter than Venus, turning night into a kind of permanent cosmic twilight. In our own neighborhood, the nearest star, beyond the sun, lies more than 4 light years away. In the crowded core of a globular cluster, the distances between stars can be smaller than the width of our solar system. If our sun lived there, we might have dozens of other stars closer than Pluto is today. In a place like that, gravity becomes a constant, restless conversation. The pulls from neighboring stars would tug at any planetary orbits, making them unstable and chaotic. Worlds might be nudged into new paths, collide, or be flung into interstellar space. It would be a beautiful environment to look at, but a difficult one for calm, long-lived planetary systems. Globular clusters are not the only star cities in the Milky Way. Scattered across the galactic disk are open clusters, younger and more loosely bound families of stars. These groups formed more recently, all from the same gas cloud, and they still carry the memory of their shared birth in their motions and chemistry. One of the most famous open clusters you can see with the naked eye is the Pleiades, the Seven Sisters, a small knot of bright stars in the constellation Taurus. To our eyes, the Pleiades looks like a handful of blue-white points, but in reality, the cluster contains well over 1,000 stars. They were all born within roughly the last 100 million years from a single molecular cloud. Open clusters like this are stellar nurseries we can watch almost in real time. Unlike the very old globular clusters, where star formation ended long ago, some open clusters are still partly wrapped in the gas and dust from which they formed. New stars may be igniting inside, while others are still quietly condensing from the surrounding material. It is like seeing a city caught in the middle of construction, cranes still raised, foundations still being poured. These young clusters, however, are not permanent. Over hundreds of millions of years, the gentle but persistent pull of the galaxy and the occasional close encounter with other stars and gas clouds gradually peel their members away. Individual stars get small gravitational kicks, drift farther from the center of the group, and eventually slip free. Most open clusters dissolve completely within about 1 billion years. their stars spreading out to become solitary wanderers, much like our own sun. For astronomers, these clusters are precious laboratories, because all the stars inside a cluster, formed at nearly the same time and from the same material, they make perfect natural experiments. By comparing stars of different masses within the same cluster, scientists can see how heavier and lighter stars age differently, how they brighten, cool, and change as their internal fuel is spent. It is like watching many versions of stellar life play out side by side. Some of the largest star clusters in the Milky Way are so full of giant suns that they earn the name superstar clusters. In these regions, there can be dozens of stars, more than 50 times as massive as the Sun, all crowded into volumes no larger than our solar system. Their radiation and fierce stellar winds crash into each other, sculpting the surrounding gas into shells and bubbles, and filling their neighborhoods with some of the most extreme conditions in the galaxy. Even so, these starry cities are just one piece of the inner galaxy's tapestry. Between them flows an invisible ocean. Space is not truly empty. It is filled with streams of gas and fine dust, flowing between spiral arms like slow, cosmic rivers. Your eyes cannot see them directly, but telescopes tuned to radio and infrared light reveal long filaments and broad currents threading through the Milky Way. These interstellar rivers carry the raw material for star formation from one region to another, quietly feeding the galaxy's ongoing life. These streams are not scattered at random. Their paths are shaped by the galaxy's rotation and gravity. As the Milky Way spins, differential rotation stretches and shears large gas clouds, drawing them out into long structures that can extend for thousands of light years. You can imagine spooning honey into a cup of coffee and giving it a gentle stir. The stirring motion creates spirals and streaks that follow the direction of the rotation. In much the same way, the galaxy's spin pulls the interstellar medium into spiral patterns and long, delicate threads. Most of the gas in these flows is simple hydrogen and helium, leftovers from the universe's earliest days, but mixed into it are heavier elements made inside stars and then scattered into space by supernova explosions. Carbon, oxygen, silicon, iron, and many other elements drift through these currents, slowly enriching different parts of the galaxy with the ingredients needed to build rocky planets and, eventually, life. Some of these rivers spiral inward toward the galactic center, feeding the bright, active regions near the core, where star formation is intense. Others flow outward toward the quieter outskirts, carrying processed material from the crowded inner galaxy to calmer regions like the one where our solar system resides. Over billions of years, this circulation has gradually redistributed elements throughout the Milky Way, blending the products of countless generations of stars. These flows are not always gentle. The interstellar medium is turbulent and chaotic, stirred constantly by stellar winds, supernova shock waves, and the gravity of massive stars and clusters. Shock waves can press on nearby gas clouds, squeezing them until they break and collapse into new stars. In other cases, those same waves heat and scatter the gas before it can condense, delaying star formation instead of encouraging it. Within these streams, temperature can vary enormously. Some regions contain hot, thin gas, heated to millions of degrees by recent supernova explosions. In others, the gas is cold and dense, tucked inside molecular clouds where temperatures fall to just a few degrees above absolute zero. Those cold clouds are the quiet nurseries where new stars are born, but they occupy only a small fraction of space. Most of the volume is filled with warmer, more diffuse gas, constantly stirred and reshaped. Magnetic fields thread through all of this, adding another layer of complexity. Though weak compared to the magnets you might hold in your hand, these galactic fields extend across vast distances and can guide the motion of charged particles, influence how gas clouds break apart and collapse, and help accelerate cosmic rays, high-energy particles that race across the galaxy at nearly the speed of light. Some of those rays eventually strike Earth's atmosphere, tiny messengers from distant violent events. As our imagined journey carries us closer to the Milky Way's center, these interstellar rivers grow denser and more excited. Gas becomes richer and more crowded, magnetic fields stronger, star formation more frequent. The calm, relatively gentle environment of our local neighborhood slowly gives way to something more restless, more intense. We are approaching regions where the galaxy's structures grow larger, where the light grows thicker, and where the balance between creation and destruction tips toward a constant roar. Ahead lies one of the galaxy's true giants, the Scutum Centaurus arm, the longest and one of the most massive spiral arms in the Milky Way. If the Perseus arm is a busy highway, this inner arm is a vast superhighway, a huge, bright lane carrying a large share of the galaxy's star formation and energetic activity. It wraps more than halfway around the galaxy, a glowing arc of stars, gas, and dust. From Earth, we glimpse only hints of this structure in the constellations Scutum and Centaurus, small patches of sky that happen to lie along its direction. The true scale is far beyond what the eye can grasp. The Scutum Centaurus arm stretches for more than 60,000 light-years and contains some of the most active star-forming regions in the Milky Way. Its position, closer to the galactic center than our own arm, means it receives a constant supply of gas and dust from the dense inner regions. This material is funneled along the arm by gravity, creating an almost continuous chain of stellar nurseries and massive clusters. The arm acts like a cosmic assembly line, steadily turning raw gas into new stars. In some parts of this arm, the rate of star formation is thousands of times higher than in our quiet local neighborhood, and many of the stars it produces are not modest suns like ours, but stellar giants, monsters with masses 50 to 100 times greater than the sun. These huge stars shine fiercely, with blue-white light that bathes their surroundings in intense radiation. They burn through their nuclear fuel in only a few million years, and then die as spectacular supernovas, sometimes bright enough to be seen from other galaxies. For a brief time, a single explosion can outshine billions of ordinary stars. Each one sends heavy elements and shock waves pouring into space, helping to shape the next generation of clouds and stars. One of the most striking sights associated with this arm is the Scutum star cloud, a bright patch of the Milky Way, visible to the naked eye. When you look at it, you are peering along a particularly dense line of sight through the arm, seeing the combined light of vast numbers of stars stacked behind one another. Within that region, astronomers have identified some of the most luminous stars known, including red supergiants, so large that, if one were placed where our sun is, its outer layers could engulf the orbit of Mars. In such a dense, active arm, gravity weaves an intricate web. Massive stars and clusters can interact in complex ways, tugging and slingshotting one another. Some stars are thrown out of their birth clusters at high speed, becoming runaway stars that hurtle through the galaxy. A few travel so fast that they will eventually escape the Milky Way entirely, gliding into the dark spaces between galaxies as solitary wanderers. Perhaps the most important role of the Scutum Centaurus arm is as a channel, a pathway that carries gas toward the galaxy's central regions. Clouds flowing along the arm's length gradually spiral inward, feeding the bulge near the core. This quiet, persistent delivery has been at work for billions of years, slowly building up the massive structures that gather around the galaxy's heart. Following these streams in our imagination, we find ourselves nearing a place where familiar patterns start to bend. The gravitational forces grow stronger, the crowding more intense, and the rate of change more rapid. We are entering a region where the normal rules that govern stars and gas in the rest of the galaxy begin to twist under the weight of something far more extreme. Deeper along the great arm we have been following, the Milky Way begins to reveal a structure that quietly rewrites our picture of what a galaxy is. At the very heart of our home, hidden behind curtains of dust, lies something astronomers only truly recognized in the last few decades. The Milky Way is not just a simple pinwheel of stars. Woven through its center is a vast, bar-shaped spine made of stars and gas, invisible to the naked eye from Earth, yet larger than anything we have crossed so far. You can imagine looking down on the galaxy from above. Instead of a neat swirl of spiral arms emerging from a round, featureless center, you would see something that looks more like a cosmic barbell. This central bar stretches for roughly 27,000 light years from end to end, about half the full diameter of the galactic disk. It is not just a loose collection of stars. It moves almost like a single piece, rotating as a solid structure, spinning faster than the more delicate spiral arms that trail from it. The bar did not appear overnight. It formed billions of years ago through a process astronomers call bar instability. As the Milky Way aged and its stars settled into more orderly, nearly circular orbits, tiny patterns of imbalance began to grow. Gravity tugged slightly more here, slightly less there, gradually stretching some orbits into more elongated shapes. Over hundreds of millions of years, those subtle patterns strengthened, aligning and reinforcing one another until they sculpted the long, rigid bar we now infer at the center. When astronomers look out into the universe, they find that this is not unusual at all. Roughly 2/3 of all spiral galaxies carry similar bars through their cores. But the galactic bar is not just a static skeleton holding the galaxy together. It acts more like a pump or a great slow paddle wheel, quietly rearranging matter on a colossal scale. As gas clouds orbit through the disk and encounter the bar's strong gravitational field, their paths are nudged away from clean circles. Instead, they are pulled into stretched, elongated orbits that tend to spiral inward. It is a little like watching water flow toward a long drain. Instead of falling straight in, the water follows curved paths, guided and twisted until it slips down the length of the channel. In this case, the drain is a bar tens of thousands of light years long. This inward flow of gas has been going on for billions of years, and its influence reaches far beyond the bar itself. By slowly feeding material toward the center, the bar has helped build up the dense clusters of stars, the thick gas clouds, and the complicated structures we now find there. Without this constant funneling action, the central regions of the Milky Way would likely be much quieter, with fewer stars and less activity. The bar's gravity does not only shape gas, it can also rearrange the orbits of stars. Those that pass too close can be jostled onto new paths, some flung inward toward the galactic center, others nudged outward toward the edge of the disk. Over time, this can mix populations of stars and slowly alter the galaxy's overall structure. Our own solar system currently resides well outside the bar's direct reach, in a safer, more distant region. But across the Milky Way's long history, countless stars have felt its grip. Recent observations have revealed that the bar is not smooth and featureless. Wrapped around its length are lanes of dense gas and dust, twisted into their own subtle spiral shapes, like filaments of a double helix coiled around a central rod. These are sometimes called bar spirals, and they are among the most active star-forming regions in the galaxy. There, the constant inflow of fresh material from the outer disk keeps the gas compressed and primed for collapse, lighting up new generations of stars over and over again. The bar's rotation is not random. Its speed is delicately tuned to the rest of the galaxy. If the bar spun too quickly or too slowly compared with the disk, the spiral arms beyond would gradually wind too tightly or unwind and dissipate over a few 100 million years. Instead, the bar's pattern speed and the disk's rotation work together, maintaining the overall spiral structure in a kind of long-lasting, dynamic balance. That balance has allowed the Milky Way to keep its familiar shape for billions of years. Following the paths carved by the bar's gravity, we move closer to the inner galaxy, where the density of stars and gas grows to truly daunting levels. Here, the space between stars changes character. Instead of isolated clouds and gentle flows, we encounter colossal molecular giants, clouds so massive they casually overshadow entire solar systems. These are not the modest nurseries of our local neighborhood. They are the heavy industry zones of the galaxy's core, where star formation happens on a scale that stretches the imagination. One of the largest of these titans is known as Sagittarius B2, a sprawling molecular cloud complex lying only a few hundred light-years from the galactic center. This single cloud holds enough raw material to build several million stars like our Sun. To bring the comparison home, imagine shrinking our entire solar system, from the Sun to the orbit of Pluto, down to the size of a small marble. Even at that scale, Sagittarius B2 would still loom larger than a stadium, a vast, shadowy bulk of gas and dust. The cloud's mass is so enormous that its gravity does not simply keep it together. It actually tugs on the orbits of nearby stars, subtly bending their paths. Inside, the conditions are worlds apart from those in our calm corner of the disk. Temperatures in many regions fall to around 10 degrees above absolute zero, making these some of the coldest natural environments known. At such low temperatures, individual hydrogen atoms can pair up, forming hydrogen molecules and creating a dense, dark fog of gas, threaded with tiny dust grains. The chemistry unfolding within these clouds is rich and strange, like a cosmic recipe book with many chapters. Astronomers have detected more than 150 different molecules in interstellar space, from simple ones such as water and carbon monoxide, to more complex organic compounds that could serve as early building blocks for life. Some clouds contain enormous amounts of ethyl alcohol. Others harbor molecules whose structures, if you could smell or taste them, would remind you of raspberries or rum. It is a quiet hint that the same chemistry that flavors fruits and drinks on Earth also plays out in the cold between stars. These molecular giants are not still. They are constantly stirred and sculpted by radiation from nearby massive stars, by shock waves from distant supernova explosions, and by magnetic fields that thread through them. Inside, turbulence reigns. Dense clumps, expanding shells, narrow filaments, and streaming flows weave a complex pattern. The clouds behave almost like weather systems on a planetary scale, with their own storms, currents, and pressure fronts. Except their air is molecular gas measured in light years. When parts of a cloud become dense enough, gravity begins to win over internal pressure and turbulence. Those regions start to collapse inward, But the collapse does not happen uniformly or all at once. Different pockets of gas give way at different times and speeds, producing a cascading wave of star formation that can last for millions of years. The most massive knots often collapse first, forming giant stars that will live short, dramatic lives. Their intense radiation and powerful winds then batter the surrounding gas, sometimes triggering new collapses in neighboring clumps, sometimes blowing them apart. The scale of star birth in these regions is staggering. A single large molecular complex can give rise to thousands of stars in one sprawling episode, assembling massive stellar associations that shine so brilliantly they can rival entire small galaxies in certain wavelengths of light. Some of the most luminous star-forming regions known in the universe are powered by clouds like these near galactic centers. As we imagine drifting ever deeper toward the Milky Way's core, the properties of these molecular titans push further into the extreme. Densities climb, gravitational forces grow stronger, and the rate at which stars could form rises to levels that would bathe any nearby planets in intense, sterilizing radiation. Here, we approach what astronomers call the central molecular zone, a ring of molecular clouds circling the galaxy's heart. It is unlike any other region we have visited. The central molecular zone spans roughly 1,000 light-years across small, when you consider the whole galaxy, yet utterly dominant in its influence. Within that relatively compact volume lies as much gas and dust as in the rest of the inner Milky Way combined. There is enough material there to form on the order of 10 million stars like our Sun, all packed into a region that occupies less than 1% of the galactic disk's surface area. If you picture our local neighborhood as having the density of thin air, the central molecular zone begins to feel more like a heavy mist, edging toward the density of water. In this simple comparison, you might expect, with so much gas packed into such a small region, that star formation would be wildly explosive here, far more intense even than in the Scutum Centaurus arm. And yet, when astronomers look closely, they find a puzzle. The actual rate at which new stars are forming in this zone is surprisingly low, 10 to 100 times lower than one would predict from the amount of available gas. Something is holding the clouds up, resisting the pull of their own gravity and slowing the usual cascade of collapse that we see in other star-forming regions. The key seems to lie in the extreme environment near the galactic center. There, intense magnetic fields, energized by the activity around the supermassive black hole and by thousands of massive stars, thread the molecular clouds like invisible bands of steel. These fields wrap through and around the gas, adding a kind of magnetic pressure that helps support the clouds against their own weight. In doing so, they can stave off gravitational collapse, preventing the familiar rapid chain of star formation from unfolding in the way it does elsewhere in the Milky Way. In this strange ring around the galactic center, when new stars do manage to form, they are often nothing like the gentle, long-lived sun that warms our skies. They are giants, some of the most massive stars known to exist. These stellar monsters can be more than 100 times heavier than our sun, burning so fiercely that they shine with a blue-white glare, bright enough to be seen from thousands of light-years away. Their lives are brief and intense. They race through their fuel in just a few million years and then end in titanic supernova explosions, disappearing almost as quickly as they arrived. The temperatures in this region carry the imprint of all that violence. Deep inside the densest cores of the molecular clouds, the gas remains bitterly cold, only a few degrees above absolute zero. But in the spaces between those clouds, the story is completely different. There, gas has been heated to millions of degrees by shock waves from ancient and recent supernovas, and by energy pouring out from the central black hole. The result is a bizarre patchwork environment where pockets of freezing cold molecular gas lie only a few light years away from bubbles of plasma so hot that atoms are stripped of their electrons. Threading through all of this are magnetic fields far stronger than anything in our quiet solar neighborhood. Their strength can reach thousands of times the values we measure near Earth. These invisible fields act like rails and slingshots, grabbing charged particles and whipping them up to extraordinary speeds. Those particles become cosmic rays, high-energy messengers that race throughout the Milky Way. A small fraction of them eventually reach our planet, colliding with the upper atmosphere and creating showers of subatomic particles that cascade toward the ground. Cosmic ray observatories on Earth listen for these faint rainstorms, decoding their energies and directions to learn about the extreme events that launch them. The central molecular zone does not only form stars, it also serves as a vast reservoir, a kind of storage tank for gas and dust. Most of the time, that material is held in a delicate balance between gravity, turbulence, and magnetic support. But when that balance is upset by a passing shockwave, by the motion of the bar, or by internal instabilities, streams of gas can begin to slide inward. They spiral along complicated paths toward the very center, feeding the region around the supermassive black hole. When that happens, bursts of activity flare to life, visible across the electromagnetic spectrum, from radio waves to X-rays and beyond. As we move inward in imagination, it feels as though we are drifting toward a point of no return. Deep in the heart of the Milky Way, something is constantly speaking, though not in any language we know. Radio telescopes on Earth pick up a steady wash of signals coming from the direction of the galactic center, whispers and shouts of electromagnetic energy that carry information about conditions no human being will ever stand in or touch. Those radio waves have traveled roughly 26,000 light-years to reach us, tiny ripples that left the core of the galaxy long before our species existed. The pattern of those signals tells a story of chaos and drama. Unlike the relatively steady radio glow from ordinary stars, the emissions from the galactic center flicker and flare. Sometimes the brightness climbs by factors of hundreds or thousands in just minutes, then slowly decays again. These changes are the radio footprints of matter falling toward the central black hole, heating up and emitting its final bursts of light and radio energy before crossing the invisible boundary from which nothing can return. The central black hole is not the only radio source crowding this region. Scattered throughout the inner few light-years are dozens of compact emitters, each one a kind of cosmic lighthouse. Some are neutron stars, the ultra-dense remnants of massive stars that exploded long ago. Others are smaller black holes, a few or several times the mass of the Sun, feeding quietly on nearby gas or even on the outer envelopes of companion stars. Each of these compact objects adds its own voice to the radio chorus. Among the most mysterious features are long, thin strands known as non-thermal filaments. These structures stretch for hundreds of light-years across the galactic center, like faint, glowing threads. They shine brightly in radio wavelengths, yet they vanish in visible light, remaining completely hidden to optical telescopes. Astronomers think that these filaments are illuminated by high-energy electrons spiraling along strong magnetic field lines, producing radio waves as they curve. But exactly how these structures form, why they are so straight and long, and what maintains them is still an open puzzle. Radio observations have also revealed the skeleton of gas movements near the central black hole. Streams of hot, ionized gas arc and curl inward, tracing the shape of the gravitational field. Instead of falling straight down, they follow looping, spiral paths, sometimes circling the black hole several times before finally crossing the point of no return. In radio images, these flows appear as curved arcs and twisted lanes, a delicate pattern drawn by gravity's hand. One of the most dramatic stories told in radio light was the fate of a gas cloud called G2. This cloud, with a mass a few times that of Earth, wandered too close to the central black hole. Astronomers watched, year after year, as G2 was stretched into a long, thin stream by tidal forces. The radio and infrared emissions from the region changed as the cloud was torn apart and heated, giving us a rare, almost live view of a small object being shredded by a supermassive black hole's gravity. The radio waves also reveal a faint, hot atmosphere around the galactic center, a halo of thin gas heated to millions of degrees by overlapping shock waves and by the energy released near the black hole. Though nearly invisible in ordinary light, this superheated gas glows in radio and X-ray wavelengths, wrapping the core in a kind of unseen fire. Perhaps most striking of all, radio studies have uncovered signs of narrow jets of matter and energy, relativistic jets emerging from near the central black hole. These jets are thin beams of particles and radiation traveling at speeds close to the speed of light, likely guided and launched by twisted magnetic fields near the spinning black hole. They shoot out above and below the galactic plane, stretching for thousands of light years, carrying energy far into the surrounding halo. Their footprints in radio light are delicate but unmistakable. Because so much dust and gas blankets the galactic center, hiding it from optical view, these radio signals are our clearest way to peer into that hidden core. They act like a set of special glasses, letting us see through the fog to the most extreme physics laboratory in our galaxy. Moving inward yet again, we finally reach a region where stars themselves are packed as tightly as people in a festival crowd. Within a space smaller than the distance from the Sun to our nearest stellar neighbor, there live more than 25 million stars. This is the nuclear star cluster, the densest stellar congregation in the Milky Way, and one of the most crowded star fields known anywhere. If our solar system was somehow placed in the middle of this cluster, the night sky would be unrecognizable. Instead of a few thousand faint stars and a handful of bright ones, you would see thousands of suns, as bright as, or brighter than, a full moon, scattered across the sky in every direction. Darkness would never truly fall. The heavens would glow with overlapping light. The stellar density here defies our everyday sense of spacing. Around the Sun, the nearest star lies more than 4 light years away. In the nuclear cluster, typical separations can be less than the radius of our solar system. In the very central regions, neighboring stars might be only a few billion miles apart, so close that their outer atmospheres can brush and interact when their orbits bring them near one another. In such an environment, planetary systems like ours stand almost no chance of surviving. Gravitational tugs from passing stars would disturb planetary orbits in just a few thousand years, flinging worlds out into interstellar space, or sending them crashing into their parent stars. And the stars here are not just ordinary suns. Many of the cluster's inhabitants are stellar exotics that form only under the most extreme conditions. There are Wolf-Rayet stars, so hot and energetic that they strip away their own outer layers in fierce winds traveling thousands of miles per second. There are red supergiants swollen to such immense sizes that, if one replaced our Sun, its surface would reach beyond Earth's orbit. There are blue hypergiants that shine with the brilliance of millions of suns combined, burning through their internal fuel so quickly that they will explode as supernovas after only a few million years of life. In this crowded and massive cluster, gravity behaves in more complicated ways than in the relatively simple setting of planets orbiting a single star. Each star feels the pull not only of the central black hole, but also of millions of neighbors. Instead of following tidy ellipses, many trace out rosette-shaped paths, their orbits precessing and twisting over time. Some stars follow extremely elongated trajectories, carrying them from the outskirts of the cluster down toward the immediate neighborhood of the black hole's event horizon, and then slinging them back out again. The cluster itself is the product of a long, complex history that has played out over billions of years. As gas flows spiraled inward along the bar and through the central molecular zone, they occasionally deposited large amounts of material into the very inner region. Each major infall event could trigger an intense burst of star formation, briefly turning the core into a stellar factory. Over time, these episodes built up multiple generations of stars with different ages and compositions. Some populations are relatively young, others are ancient, survivors from much earlier times. Here, stellar lifetimes are compressed. Massive stars are born, live, and die all within a few million years. Their supernova explosions send shock waves through the cluster, add heavy elements to the gas, and help shape the next generation of stars. Mixed in among the bright, living suns are the remnants of previous generations. Dozens or perhaps hundreds of stellar mass black holes, neutron stars, and white dwarfs, all sharing the same crowded volume. When these compact objects pass close to one another, gravity can draw them into tight pairs. Over time, they may spiral together and merge, releasing brief but powerful bursts of gravitational waves, ripples in space-time itself that travel outward across the universe. In this sense, the nuclear star cluster acts like a natural particle accelerator and collision chamber, constantly sending stars and remnants into new, energetic encounters. The same dense environment that crushes planetary systems also creates stellar slingshots. Some stars that pass very near the central black hole or experience strong gravitational encounters with other massive objects are flung outward at tremendous speeds. A few are accelerated to more than 1,000 miles per second, fast enough to break free of the Milky Way's gravitational grip altogether. These hypervelocity stars have been detected far out in the galaxy's halo, racing away from the center like sparks thrown from a fire, silent witnesses to the violence of their birthplace. In the very middle of this maelstrom lies the source of much of the chaos, the Milky Way's supermassive black hole. At the absolute center of our galaxy lurks this invisible giant, known as Sagittarius, A star. It contains the mass of roughly 4 million suns, compressed into a region smaller than the orbit of Mercury around our star. This dark object sits almost perfectly still at the bottom of the galaxy's gravitational well, while roughly 200 billion stars, along with countless clouds and clusters, orbit around it like moths circling an unseen flame. It is the anchor that helps hold the Milky Way together. For a very long time, astronomers had a strong suspicion that a monster was hiding at the center of the Milky Way, but they could not prove it. The galactic core is buried behind thick curtains of dust that block visible light, making direct observation impossible. In the 1990s, that veil began to lift. Using infrared telescopes that could peer through the dust, astronomers started tracking individual stars near the galactic center. What they saw changed our understanding of black holes forever. The stars closest to Sagittarius A star move in orbit so tight and so fast that they stretch the limits of what we thought stars could do. One of them, a star known as S2, completes a full loop around the black hole in only about 16 years. At its closest approach, it swings past Sagittarius A star at over 25 million miles per hour, fast enough to cross the distance from Earth to the Moon in roughly half an hour. In that region, gravity is so intense that the star's motion shows subtle effects predicted by Einstein's theory of general relativity. Its orbit precesses, its light is redshifted, and time for it does not pass quite the same way as it does for us. Sagittarius A star itself does not blaze constantly. Most of the time it appears relatively quiet, a dark heart wrapped in a soft glow. But every so often, a patch of gas or a stray fragment of debris wanders too close. As that material spirals inward, it is compressed and heated to incredible temperatures, reaching billions of degrees. In those moments, the black hole flares. Its brightness can increase by factors of hundreds within minutes, briefly outshining all the stars in the nuclear cluster around it before fading again. These feeding events are the last cries of matter as it gives up its energy and disappears beyond the horizon. The event horizon of Sagittarius A star, the boundary beyond which nothing can ever return, has a diameter of about 15 million miles. That sounds enormous, yet it is tiny compared with a black hole's true realm of influence, which extends for several light years in every direction. Within that larger sphere, the gravity of Sagittarius A star dominates the motions of stars and gas, quietly steering their orbits and even bending the paths of light. In recent years, the most remarkable evidence of all came when astronomers managed to capture a direct image of the black hole's shadow. Using the Event Horizon Telescope, a planet-sized array of radio observatories linked together, they stitched data from around the world into a single, sharp view. The result was a glowing ring of superheated gas surrounding a dark central patch, the silhouette of the event horizon itself. That image matched decades of theoretical predictions and gave us our first visual confirmation of what a supermassive black hole should look like. Around Sagittarius A star, the magnetic field is extraordinarily strong, millions of times stronger than Earth's magnetic field. This intense magnetism whips charged particles up to nearly the speed of light and helps launch them into thin jets that shoot out above and below the galactic plane. Those jets extend for thousands of light years, carrying energy and matter far from the center and influencing how gas moves and how stars form in regions that the black hole's gravity alone could never directly reach. Every star in the Milky Way, including our Sun, ultimately orbits this central giant. Even though we sit roughly 26,000 light-years away, the gravity of Sagittarius A star helps guide our path through space. It is the anchor at the bottom of the galaxy's gravitational well. The event horizon itself marks a kind of ultimate frontier, a surface where our familiar rules begin to unravel. It is the edge of everything we can see or know about what happens to matter once it falls in. Crossing it means leaving the visible universe behind. The horizon is not a solid shell you could touch or stand upon. It is a mathematical boundary, defined by gravity so strong that the escape velocity there exceeds the speed of light. Since nothing can move faster than light, nothing inside that radius can climb back out. To us, the horizon appears as a perfect sphere encasing the black hole, with a diameter of roughly 15 million miles, large enough that, if Sagittarius A star sat where our Sun is, the orbits of Mercury and Venus would fit neatly inside it. Yet the strangest part is how perspective changes what you would experience near that boundary. For an observer far away, watching you fall in, your motion would seem to slow as you approach the horizon. Your signals would be stretched to longer and longer wavelengths, sliding into redder and then invisible light until you appear to freeze at the edge and fade away. From their viewpoint, your final approach would take an eternity. Time dilation would stretch your last moments almost without limit. From your own perspective, however, the story would be very different. You would feel yourself falling inward, and if the black hole were large enough, you might notice nothing special at the moment you crossed the horizon. There would be no bright line, no barrier, no jolt. You would simply pass through empty space that happens to have a special property. Beyond that point, every possible direction you could go would lead deeper inward. Even if you tried to fire rockets outward, space-time itself would be curved so that your future still points toward the center. Closer still to the black hole, space is warped so severely that ordinary intuition fails. Tidal forces become extreme. The difference in gravity between your feet and your head, or between one end of a spacecraft and the other, grows enormous. If you ventured too near, the pull on the part of you closest to the black hole would be much stronger than on the farthest part, stretching you into a long, thin shape before tearing you apart at the atomic level. Astronomers call this process spaghettification, a strangely playful word for something unimaginably violent. Time itself is twisted here. The intense gravitational field near the horizon slows the passage of time relative to regions farther away. A clock hovering just outside the event horizon would tick more slowly than an identical clock far out in normal space. This gravitational time dilation means that, in a sense, the black hole and the environment immediately around it exist in a different temporal frame from the rest of the galaxy. Deeper still, the curvature of space-time becomes so extreme that our current theories can no longer describe it. At the very center of the black hole, equations predict a singularity, a point where density becomes infinite, and where the laws of physics, as we understand them, break down completely. The event horizon acts as a shield, preventing this region from being directly exposed to the rest of the universe. Whatever truly happens there remains hidden. Some modern ideas in theoretical physics suggest that the horizon might not be an absolutely perfect one-way barrier. Quantum effects could allow tiny amounts of information to leak out over immense stretches of time through a process known as Hawking radiation, in which black holes slowly lose mass by emitting faint particles. But for a supermassive black hole like Sagittarius A star, this effect is so minuscule that it is essentially impossible to detect with present-day instruments. Beyond the horizon lies territory that presses hard against the limits of what we can even imagine. Yet the black hole does not only influence the universe by swallowing matter, it also shapes its surroundings in more visible, dynamic ways. From the region around Sagittarius A star, two narrow, invisible cones of energy and particles pierce space, moving at speeds close to the speed of light. These relativistic jets extend for thousands of light years, above and below the plane of the galaxy, carrying matter and energy far from the black hole's immediate grip. They are among the most dramatic expressions of power in the cosmos. Their origin is particularly intriguing because, in theory, nothing can escape from inside the event horizon. The jets do not. They are born just outside it, in the swirling accretion disk of superheated gas and plasma spiraling toward the black hole. As this material falls inward, it is squeezed and heated to temperatures hotter than the cores of ordinary stars. Magnetic fields threading through the disk become twisted and amplified by the motion, wound up like rubber bands being turned tighter and tighter. At some point, those magnetic field lines snap into new configurations, releasing energy and flinging charged particles outward along narrow channels above the disk's poles. The result is a pair of focused beams, remarkably straight and narrow. even over thousands of light years. No human-made technology can match their precision or their power. By the standards of more active galaxies, the jets from Sagittarius A star are modest. There are supermassive black holes elsewhere, whose jets are so intense that they can be seen from billions of light years away and can outshine all the stars in their host galaxies. Our own galaxy's central black hole is currently in a relatively quiet phase. Its jets are faint and subtle, detectable only with very sensitive instruments. Even so, they carry enormous energy. Particles within these jets can be accelerated to energies millions of times higher than those reached in human-built particle accelerators. As they race along, they interact with magnetic fields and with the thin gas they encounter, producing gamma rays, the most energetic form of electromagnetic radiation, as well as high-energy cosmic rays that occasionally strike Earth. For the particles themselves, time runs strangely. Traveling at nearly the speed of light, they experience strong time dilation. A journey that takes thousands of years in our frame might feel like minutes or hours to them. Observations suggest that the jets from Sagittarius A star do not always point in exactly the same direction. Over thousands of years, the rotation axis of the black hole may slowly wobble, causing the jets to sweep out new paths, like the spray from a slowly turning sprinkler. Where those beams meet the surrounding interstellar medium, they drive shockwaves into nearby gas clouds, heating and stirring them. This injected energy can prevent some clouds from collapsing into new stars, or, in other situations, compress parts of them and subtly influence where and when star formation happens. In this way, the jets act as long-reaching arms of the black hole's influence, regulating the flow of gas and the birth of stars far beyond the immediate neighborhood of the event horizon. Close to Sagittarius A star, the idea of time itself becomes flexible. The black hole's immense gravity warps space-time so profoundly that distances, durations, and even the sequence of events depend on where you stand. Here, Einstein's most counterintuitive predictions stop being abstract equations and become the everyday physics of the environment. Gravitational time dilation means that clocks tick at different rates depending on how deep they sit in the gravitational field. A clock placed just outside the event horizon would run significantly slower than an identical clock far out in the galactic disk. From our vantage point, 26,000 light-years away, that near-horizon clock would seem almost frozen. Its seconds would stretch out as redshift dims any signal it sends, until its motion fades from view. Near the edge of the horizon, this effect grows without limit. To a distant observer, anything falling towards Sagittarius, a star appears to slow more and more as it approaches the boundary. Its light is stretched to longer wavelengths, its image dims, and it seems to hang at the brink, caught at the edge of forever, never quite crossing, even though, in its own frame, it has already slipped beyond the point of no return. The bending of time around Sagittarius A star does not stop at the event horizon. Its influence reaches far out into the cluster of stars that circle close to it. Those stars live in a different rhythm from the rest of the galaxy. The star we met earlier, S2, which loops around the black hole roughly every 16 years, does not age at the same rate it would if it orbited in a quieter, more distant region. Because it spends its life deep in the black hole's gravitational well, its time runs just a little slower. Over millions of years, that tiny difference could add up to thousands of extra years of stellar lifetime. Like a clock that lags by only a fraction of a second each day, but eventually falls far behind. This warping of time is inseparable from the warping of space. Near the black hole, space-time itself curves like a stretched rubber sheet with a heavy bowling ball. placed in its center. The analogy is simple, almost childlike, but it captures the essence. Anything moving nearby must follow the dip. Straight lines in ordinary space become curved paths near the black hole. For both light and matter, photons that would normally travel in straight trajectories are bent, their paths arcing around the mass. Gas clouds, stars, even whole clusters are forced to follow the geometry carved into the fabric of space-time. One of the most mind-bending consequences of this extreme curvature is the theoretical possibility of closed time-like curves paths through space-time that loop back on themselves. Near certain kinds of rotating black holes, the equations of general relativity allow for trajectories where, in principle, an object could travel through space and return to a point in its own past. It sounds like science fiction, and in practice, these paths would exist only in the most violent gravitational environments we can imagine, places filled with energies and tidal forces strong enough to tear any known form of matter apart. Still, the fact that the mathematics even permits such curves hints at how strange the rules become near these objects. The bending of time and space around Sagittarius A star also leaves its mark on the light we receive from that region. Radio waves coming from gas clouds spiraling inward arrive at Earth with their frequencies shifted by the black hole's gravity. This gravitational redshift stretches the waves to longer wavelengths, and by measuring that shift, astronomers can directly infer the strength of the gravitational field and estimate the black hole's mass. In this way, time dilation and redshift become tools, quiet signatures written into the radiation that travels across tens of thousands of light years to reach our instruments. Some ideas in modern cosmology go even further, suggesting that the extreme space-time curvature near supermassive black holes might be linked, in subtle ways, to the behavior of the universe on its largest scales. There are speculative theories in which the physics around black hole horizons connects to the expansion of space itself, tying together the smallest and largest arenas of cosmic evolution. These ideas are still tentative, but they underline a deeper point. What happens in the shadow of a black hole may echo through the fabric of the cosmos. If we gently pull our view back from this region where time bends and nearly breaks, we begin to see the galaxy as a whole again. And when we do, another, even larger mystery comes into view, one that surrounds everything we have been talking about so far. Our entire galaxy lives inside something invisible and strange. Beyond the familiar glow of stars and the faint shimmer of gas clouds, the Milky Way is wrapped in a vast, spherical halo of dark matter. This hidden substance outweighs all the normal matter we can see by roughly a factor of 10 to 1. It extends far beyond the furthest spiral arms, forming an unseen scaffold that holds the galaxy together and shapes how it moves through the universe. Dark matter does not emit light, does not absorb it, and does not reflect it. It is transparent to every form of electromagnetic radiation, from long, lazy radio waves to fierce gamma rays. We know it exists only because of its gravity. When astronomers measure how fast stars in the outer regions of galaxies orbit their centers, they find that those stars move too quickly to be held by the pull of visible matter alone. Something else, something massive and unseen, must be adding extra gravity to keep them bound. In the Milky Way, this dark halo is enormous. It stretches out to distances of at least 600,000 light-years from the galactic center, roughly 3 times larger than the visible disk of stars and gas. It is big enough to encompass several of our smaller companion galaxies. If you could somehow see dark matter, the Milky Way would look like a luminous, thin disk suspended at the center of a much larger, softly glowing sphere. This invisible halo is heavy. It holds the equivalent of roughly 1 trillion solar masses in dark matter, making it by far the most massive part of our galactic system. All of the stars, gas, dust, and planets. You can see every glowing nebula, every cluster, every world add up to only about 15% of the total mass. In a sense, we live inside a dark matter structure, with normal matter sprinkled through it like a light seasoning on a much larger cosmic dish. The halo is not perfectly smooth. Computer simulations that try to follow the growth of structure in the universe suggest that dark matter forms clumps and streams inside the larger halo, like eddies and currents in a deep ocean. Some of these lumps may be the leftover cores of small galaxies that were torn apart long ago by the Milky Way's gravity. Others might be primordial, formed in the very early universe, before the first stars ignited, and still drifting through the halo as ancient fossils of the cosmos's youth. Despite its importance, the true nature of dark matter remains one of the most stubborn mysteries in science. Leading ideas point to exotic particles that barely interact with normal matter at all, except through gravity and the weak nuclear force. They would sail through solid objects, planets, even stars, almost as if nothing were there. Laboratories around the world are searching for tiny, rare interactions between these particles, and detectors buried deep underground or cooled to near absolute zero. So far, dark matter has kept its secret, living up to its name. The dark halo has shaped not just the present-day galaxy, but its entire history. In the early universe, before galaxies like the Milky Way existed, dark matter began to clump under its own gravity. These clumps formed gravitational wells, invisible basins into which normal gas could fall. Over time, gas collected in those wells, cooled, and began forming the first generations of stars and proto-galaxies. Without this dark scaffolding, the matter we can see would have been too smoothly spread out for galaxies to condense as quickly as they did. The Milky Way is, in a very real sense, a luminous structure hanging within a far more massive dark framework. As our solar system orbits the galaxy, it moves through this dark halo, creating what you might think of as a wind of dark matter particles flowing past us. They stream through the solar system at hundreds of kilometers per second, passing through planets, moons, and even our own bodies undetected. We do not feel them. We cannot see them, yet they are among the most abundant forms of matter in the universe, brushing by us every moment. Beyond the edge of this halo, the structures of the universe grow even grander. But even before we step out that far, we find that our galaxy is not an isolated island. It has company, a small swarm of companions orbiting it, caught in its gravitational field. Around the Milky Way, like moons circling a planet, dozens of smaller galaxies follow elongated paths. These satellite galaxies range in size from tiny collections of a few million stars to substantial systems holding billions. Together, they form a complex gravitational community that has been evolving and interacting for billions of years. The most famous of these companions are the Large and Small Magellanic Clouds, visible from the southern hemisphere as faint, fuzzy patches in the night sky. The Large Magellanic Cloud hosts roughly tens of billions of stars, making it about 1/10 as massive as the Milky Way. Its smaller companion carries on the order of a few billion stars, still large enough to sustain active star formation and to maintain a modest spiral pattern of its own. But these two bright companions are only the most obvious members of a larger family. Astronomers have identified more than 50 smaller satellites orbiting the Milky Way, with names like Draco, Ursa Minor, and Sagittarius. Most are dwarf galaxies, containing anywhere from a few thousand to a few billion stars. They are scattered across the sky in many directions, some as close as roughly 75,000 light-years from the galactic center, others reaching out to distances of around 3 million light-years. The relationship between the Milky Way and its satellites is intricate and often harsh. Our galaxy's stronger gravity pulls on these smaller systems, stripping away gas and stars from any that wander too close. The Sagittarius dwarf galaxy, for example, is currently being shredded by this process. Long streams of its stars have already been drawn out, forming tidal tails that wrap around us and appear as faint, elongated structures in our sky. Over hundreds of millions of years, those streams will blend into the Milky Way's outer regions, their original galaxy dissolved and absorbed. Some satellites bear scars of repeated encounters with our galaxy. Their star populations show evidence of multiple bursts of star formation, triggered when their orbits brought them close enough for the Milky Way's gravity to compress their gas clouds. As they swing through these close approaches, tides squeeze the gas, prompting it to collapse into new stars. Then they drift away again, only to return on another long, slow orbit. The ages of the stars inside these dwarfs become like geological layers, recording each close pass. Satellite galaxies are also valuable windows into the nature of dark matter. Many appear to be overwhelmingly dominated by it, with their visible stars contributing only a small fraction of their total mass. Some are so rich in dark matter and so poor in ordinary material that they barely have enough gas to form stars. They exist as almost invisible gravitational ghosts, with just a small handful of dim stars betraying their presence. Interestingly, the satellites are not arranged in a completely random way around the Milky Way. Instead of forming a roughly spherical shell, many lie in a flattened, disc-like arrangement. This surprising pattern has challenged standard models of how galaxy groups assemble, which often predict a more isotropic distribution. It hints that the early universe and the way our galactic neighborhood formed may have been more structured and organized than we once believed, with preferred directions and patterns woven into its very beginning. Our family of companion galaxies is not fixed in stone. It changes quietly over time as we discover new, fainter members and as existing ones are slowly torn apart by gravity. Deep surveys of the sky have revealed extremely dim satellites that are barely brighter than large star clusters, ghostly systems that push the limits of what we even call a galaxy. Some are little more than a handful of stars bound together by an oversized halo of dark matter. Yet even this retinue of satellites is small, compared with the vast rivers of gas and debris that thread between them and our own galaxy. Trailing behind the Magellanic Clouds, like a pale contrail behind an aircraft, stretches one of the largest structures associated with the Milky Way. The Magellanic Stream is a great river of hydrogen gas arcing across the sky, more than 600,000 light-years long, longer than the diameter of the entire galactic disk itself. This enormous streamer tells the story of a slow-motion encounter that has been unfolding for billions of years. The stream formed through gravitational theft on a galactic scale. As the large and small Magellanic Clouds orbit the Milky Way, our galaxy's stronger gravity pulls on their outer layers, stripping away gas and even some stars. The stolen material does not simply drop straight into the disk. Instead, it is stretched thin into tidal tails that trace the curved orbital paths of the Magellanic Clouds through space. Closer examination shows that the Magellanic Stream is not just a single tail. It is a tangled network of multiple gas streams, some flowing inward toward the Milky Way, others being flung outward into the space between galaxies. The mutual gravity of the large and small Magellanic clouds adds to the complexity, as they tug on one another while simultaneously losing material to the Milky Way's tides. They pull gas back and forth, braiding the stream into overlapping filaments. Altogether, the Magellanic Stream holds enough gas to build roughly 2 billion stars like our Sun. That is more raw material than many entire small galaxies possess, stretched out across hundreds of thousands of light years. Over the next few billion years, much of this gas will gradually fall into the Milky Way's disk, raining down in slow motion and sparking new rounds of star formation. Long after tonight, and long after us, the stream will still be feeding our galaxy. What makes this structure even more striking is its chemical fingerprint. The gas stripped from the Magellanic Clouds contains fewer heavy elements than the gas in the Milky Way's disk. It is relatively pristine, closer in composition to the early universe. When this cleaner gas mixes with our more processed material, enriched by many generations of stars, it dilutes the concentration of heavy elements and provides fresh, cool fuel for new stars. This quiet, ongoing recycling helps explain how the Milky Way can keep forming stars billions of years after it was born. The stream does not carry only ordinary matter. Dark matter, too, is torn from the halos of the Magellanic Clouds and dragged along with the gas. This invisible component helps hold the streams together and shapes the paths they follow. Computer simulations suggest that such dark matter streams from disrupted satellites may be responsible for some of the fine structure we see in the Milky Way's larger dark halo, like faint ripples in a pond we cannot see directly. For astronomers, the Magellanic Stream is more than a curiosity. It is a measuring tool. The exact shape, thickness, and motion of the stream depend sensitively on the total mass of the Milky Way and on how that mass is distributed. By mapping the stream in detail, how it curves, how fast it moves, how its density changes, researchers can weigh our galaxy and test ideas about the behavior of dark matter. It is like tracing the pattern of leaves in a river to learn about the rocks and currents hidden beneath the surface. And the Magellanic Stream is not alone. Similar tidal streams from other disrupted dwarf galaxies lace through the outer halo, wrapping around the Milky Way in faint arcs. Each one is a fossil of a past encounter, evidence that the growth of our galaxy is not a single ancient event, but an ongoing process of merging and accretion that continues, slowly, even now. All of these gradual changes, though, are small compared with the grand meeting that awaits us in the distant future. On timescales that dwarf human history but are still short compared with the full life of the cosmos, our sky will be transformed. Roughly 4.5 billion years from now, the familiar pattern of constellations will have long since shifted, and something huge will loom in the night: the Andromeda Galaxy. Even today, it is already on its way, hurtling toward us at about 250,000 miles per hour. Eventually, the two great spirals of the local group, the Milky Way and Andromeda, will collide in what may be the most spectacular event our galaxy will ever experience. This impending collision will reshape both galaxies. Stars will be tossed into new orbits, whole regions of gas will be compressed and heated, and the rate of star formation may surge to the highest levels either galaxy has ever seen. Despite the word collision, though, individual stars are so tiny compared with the distances between them that direct star-star impacts will be exceedingly rare. Most stars will simply pass by one another, carried along by shifting gravitational tides. What truly collides are the gravitational fields, the great disks of gas, and the extended dark matter halos. Their interaction will completely transform the overall structure of both galaxies, but it will happen slowly, over hundreds of millions of years, like a dance in extreme slow motion. Andromeda is the heavyweight in this encounter. It contains on the order of 1 trillion stars, compared with the Milky Way's roughly 400 billion. It is also approaching on a nearly head-on course, rather than skimming past, which will make their meeting more dramatic than if they brushed one another in a glancing blow. Computer simulations of the future show that during the first close pass, gravity will fling long, bright streams of stars out into intergalactic space, forming tidal tails that can stretch for hundreds of thousands of light years. At the centers of both galaxies, their supermassive black holes will begin their own slow dance. As the galaxies interpenetrate and their cores sink toward one another, these central monsters will orbit together, spiraling inward as they lose energy to surrounding stars and gas. In their final moments, as they draw close, they will generate powerful gravitational waves, ripples in space-time that will race outward across the universe. The final merger will release more energy in gravitational waves than all the stars in both galaxies shine in light over the same period. Our own solar system will likely survive this reshaping. The chance of a direct collision with another star is tiny. However, our position within the merged galaxy will almost certainly change. The sun may be flung out toward the new galaxy's outskirts, or it might end up on a different orbit, perhaps closer to the center than before. Either way, by the time this happens, our sun will be nearing its own red giant phase. Earth's surface will long since have become inhospitable, its habitability compromised by changes in the sun rather than by the galactic collision. The encounter will compress vast clouds of gas, where the two galaxies overlap, triggering intense bursts of star formation. These starbursts will light up the sky of the merged system with billions of newly born stars, turning the remnant into one of the brightest objects in the local universe. For a time, the rate of star formation could increase by factors of hundreds compared with current levels in either galaxy. Astronomers have already given a name to this future child of the collision: Milky Way, a blend of Milky Way and Andromeda. The merged galaxy will probably not be a spiral. The orderly rotation of both parent disks will be disrupted, their spiral arms shredded. Instead, Milky Way will likely settle into an elliptical shape, a more rounded, puffed-up galaxy, containing the combined stellar populations of both parents, along with their dark matter halos and their merged central black hole. Even this grand collision, though, is only one chapter in a far longer story. Larger forces are at work on scales beyond any single galaxy, and as the universe continues to expand and evolve, our galactic home faces a future that is anything but eternal. Over time spans so huge that they dwarf even the time until the Andromeda collision. The Milky Way, whatever its future name and exact shape, will slowly fade. Its stars will burn out one by one, leaving behind a quieter population of remnants: white dwarfs, neutron stars, and black holes drifting through an ever-expanding cosmos. The death of our galaxy will not be a single event, but a drawn-out dimming over trillions of years. In a sense, that process has already started. The first stage of a galaxy's slow decline is a drop in its star formation rate. For billions of years now, the Milky Way's rate of turning gas into new stars has been gradually decreasing as its supply of fresh gas is used up or blown out into space by stellar winds and supernova explosions. Much of the hydrogen and helium that was once available has already been locked into stars or expelled into intergalactic space. Within roughly 10 billion years, current models suggest that our galaxy will largely stop forming new stars. It will become what astronomers sometimes call a red and dead system. populated mostly by older, cooler stars. As star formation ceases, the stellar population will age. The massive, bright blue stars that dominate young regions today will have long since exploded. Sun-like stars will go through their red giant stages, shedding their outer layers and shrinking into white dwarfs. Gradually, the overall light of the galaxy will grow redder and dimmer as only small, long-lived stars remain active. Red dwarf stars, the most common type of star in the Milky Way, can burn for extraordinarily long times, stretching into trillions of years. They will be the final embers, the last steady lights shining in the fading galaxy. For ages beyond anything our minds can comfortably hold, these tiny stars will provide faint warmth to any lingering worlds. But even they cannot burn forever. Eventually, they too will exhaust their nuclear fuel, cool, and transition into dark, degenerate objects, black dwarfs, cold and faint. As this stellar aging continues, the supermassive black hole at the center will take on a more dominant role. With little fresh gas available to form new stars, any remaining gas and stray matter will slowly spiral inward. Stars that wander too close to the central region may be torn apart by tidal forces, briefly flaring as their material is accreted. Over an enormous span of time, the central black hole could swallow a substantial fraction of the galaxy's remaining mass, quietly growing even as everything else grows dimmer. On still longer timescales, the expansion of the universe, driven by dark energy, will reshape the context in which our faded galaxy drifts. As space itself expands faster and faster, galaxies that are not gravitationally bound to us will recede beyond our horizon, disappearing from view. Eventually, even structures that are currently bound may be affected, depending on the exact nature of dark energy. Star systems that once shared a common galaxy could find themselves carried apart by the stretching of space-time, isolated in a cold, dark void. The final act of our galaxy's story involves the slow evaporation of its remaining black holes through Hawking radiation. According to quantum theory, black holes are not perfectly black. Over unimaginable lengths of time, they leak energy in the form of tiny particles. This process causes them to lose mass and shrink. For stellar mass and supermassive black holes, the timescales involved are almost beyond comprehension. Measured in Google years are 1 followed by 100 zeros, a number so vast that there are more zeros in it than there are atoms in the observable universe. When the last black hole finally evaporates, releasing its remaining energy in a final whisper of radiation, the Milky Way as a bound, meaningful structure will be gone. What remains will be thin, cold radiation and a sparse sprinkling of elementary particles drifting through an ever-expanding, increasingly empty cosmos. Maybe death is not the right word for what awaits our galaxy. Nothing truly disappears. The matter and energy that once made up the Milky Way will linger in new forms, drifting into other structures in a universe we can barely picture. The carbon, oxygen, and other heavy elements forged in our stars will still exist, scattered and waiting, ready to become the raw material for whatever comes next. Even in its fading, our galaxy will simply be changing shape inside a much larger story. Because the Milky Way, for all its beauty, is small by some cosmic standards. Scattered through the darkness are galactic giants so vast that our home is little more than a luminous seed beside them. Some of these behemoths contain hundreds of trillions of stars, stretch for millions of light years, and harbor black holes massive enough to swallow our entire solar system millions of times over. One of the largest known galaxies is called IC 1101. a giant elliptical system, over 5 million light-years, from end to end. The distance between the Milky Way and the Andromeda Galaxy could fit inside it more than 20 times. IC 1101 may hold on the order of 100 trillion stars, making it perhaps a few hundred times more massive than our galaxy. If the Milky Way were the size of a basketball, that galaxy would be larger than a stadium built around it. Other galaxies are monstrous, not in size, but in brightness. Quasars are galaxies whose central black holes are greedily feeding on enormous amounts of gas and dust. As material spirals inward, it heats up and blazes so fiercely that the combined light of the accretion disk can outshine thousands of ordinary galaxies. The black holes at their hearts can contain tens of billions of solar masses, turning their surroundings into dazzling beacons that we can see from billions of light years away. In the Phoenix cluster, for example, the central galaxy is forming new stars at a rate hundreds of times higher than the Milky Way. It is converting gas into suns so quickly that it could add the equivalent of several solar masses every single day and double its stellar population in just a few 100 million years. It is a reminder that not all galaxies are settling into quiet middle age. Some are still in wild, brilliant youth. On an even larger scale, there are galaxy clusters, enormous gatherings of galaxies bound together by shared gravity. The Coma cluster contains more than 1,000 sizable galaxies and many thousands of smaller ones, all held in an enormous dark matter halo, whose total mass reaches into the realm of 1,000,000 billion suns. These clusters are among the largest structures in the universe that are still gravitationally bound, rather than being pulled apart by the expansion of space. Some of the strangest giants are the ones that should not exist so early. Astronomers have found fully grown, massive galaxies dating back to when the universe was less than 1 billion years old. Somehow, these systems managed to assemble huge populations of stars in a fraction of the time our models would expect. Their very existence pushes us to rethink how quickly matter can gather and how efficiently stars can form. Many large galaxies grow through a quieter kind of violence, cosmic cannibalism. They merge with and gradually absorb smaller companions, adding their stars and dark matter to their own. The galaxy known as M87 shows evidence that it has eaten dozens of smaller systems over billions of years, building up a mass of several trillion suns through this slow, steady feasting. Our Milky Way, with its roughly 400 billion stars and graceful spiral arms, is modest by comparison, a well-behaved citizen in a universe that also contains true gluttons. Stepping back from individual galaxies and clusters, we can trace our place in a nested series of homes. Like an address written on the side of the cosmos, it begins simply, Earth orbiting an ordinary star. That star sits inside our solar system, which drifts through a cavity of hot, thin gas known as the local bubble. The local bubble lies within the Orion Arm, a minor spiral arm of the Milky Way galaxy. The Milky Way itself belongs to the local group, a gathering of more than 80 galaxies dominated by the Milky Way, Andromeda, and the smaller Triangulum galaxy. Together, these systems fill a volume about 10 million light-years across, and contain on the order of a few trillion stars. The local group, in turn, occupies the outskirts of the Virgo cluster, a larger collection centered roughly 54 million light-years away. The Virgo cluster contains more than 2,000 galaxies, including giants like M87, with its supermassive black hole of several billion solar masses. Our little group is slowly falling toward Virgo, pulled by its combined gravity. Even that is not the end of the address. The Virgo cluster sits inside the Virgo supercluster, sometimes called the local supercluster, a sheet-like arrangement of clusters and galaxies stretching across roughly 110 million light-years and containing perhaps 100,000 galaxies. For a time, it seemed this might be the natural top of our local structure. Then astronomers discovered that the Virgo supercluster is itself only a branch of something larger, now called Laniakea, a Hawaiian word meaning immense heaven. Laniakea is a supercluster of superclusters, extending some 500 million light-years and containing the equivalent of 100 million billion suns in stars, gas, and dark matter. At its heart lies a region we call the Great Attractor, whose gravity is drawing our entire local group toward it at speeds of over 1 million miles per hour. From there, the pattern continues outward. Laniakea connects to other superclusters through enormous filaments of dark matter and galaxies, forming the cosmic web that spans the observable universe. Between these filaments lie vast voids, almost empty regions where galaxies are sparse. Some of these voids are so large that light takes hundreds of millions of years to cross them. On this scale, our entire galaxy is a tiny knot in a thread of a single strand, in a much larger tapestry. If we write our full cosmic address, it might sound like this: Earth, Solar System, Local Bubble, Orion Arm, Milky Way Galaxy, Local Group, Virgo Cluster, Local Supercluster, Laniakea Supercluster, Observable Universe. Each line names a home that contains billions or trillions of stars, and we occupy just one of them. Knowing this does not make us smaller. It gives context to our smallness. The journey we have traced from our local bubble to the galactic center, out through the halo, and into the surrounding web marks only one tiny thread in all this structure. Yet along that thread, on one rocky planet circling one ordinary star, matter has arranged itself into a form capable of noticing, measuring, and wondering. Every atom in your body carries that story. The calcium in your bones was forged in the hearts of massive stars and scattered by supernova explosions. The iron in your blood was cooked in stellar cores and hurled into space when those stars died. The oxygen in your lungs was made in earlier generations of suns and shared with the universe through stellar winds. You are literally assembled from the ashes of long-dead stars and enriched by the life cycle of the galaxy itself. At the same time, some of the most important pieces of the story remain hidden. Dark matter outweighs visible matter by about 10 to 1, yet we do not know what it is made of. Dark energy, an even more mysterious component, seems to be driving the expansion of the universe to accelerate, stretching the cosmic web faster and faster. The supermassive black hole at our galaxy's heart behaves according to equations that push our understanding of physics to its edge, where space and time curve into shapes our minds struggle to picture. We live in an era when these mysteries are not just philosophical. Instruments can now listen for gravitational waves, catch the flicker of starlight bent by planets, and image the shadow of a black hole. Space telescopes like the James Webb Observatory are revealing galaxies from when the universe was young, while observatories on Earth track individual stars as they whirl around Sagittarius A star. Each new measurement narrows our ignorance by a tiny amount. For now, as you imagine the Milky Way from its quiet outskirts to its radiant core and out into the filaments that bind it to countless other galaxies, you can hold one simple thought. You do not merely live in the universe. You are part of the universe, arranged in such a way that it can look back on itself and ask questions. In understanding our galaxy's place in the cosmos, we begin to understand our own.